Hi there. We're going to give it a minute. We're just going to give it a minute for other people to show up, and then we'll start. We have some things I want to talk about for next week, but I want to wait for other people, and then I'll put out an announcement later too. How's it going? I know, can you believe it? We're wrapping up. We have today and tomorrow for chapter 3.3, and that's it for material. It's kind of wild. We'll see how much we get through today. We may, if we get through all the lecture stuff, then we'll do classwork tomorrow. I may break it into 2 pieces. We'll kind of decide. And then next week, let's see, next week what I'd like to do is, I was thinking about it, and I'm open for input. Monday, we have 2 quizzes. And usually when I'm teaching this class in person, sometimes we tend to vote on having the 2 quizzes at the same time instead of, kind of doing presentations on Monday and a quiz, and then presentations on Wednesday and a quiz. We usually do 2 quizzes on Monday, and then all the presentations on Wednesday. So if we are going to do 2 quizzes on Monday, you get the whole class period. And so what I was thinking I might like to do is make the quizzes available during the class time period, because I don't plan to teach, obviously, because we would have both quizzes. So make the quizzes available during what would be our normal class time, okay? And then you guys can log in during our normal class time and take the quizzes, but it'll still be a 24-hour window. So if the class time doesn't work for you, you can take them, within that 24-hour window. So you'll have the 65 minutes to do the quizzes plus 15 minutes each, right, to take a picture and upload it. Okay, so I'm going to set up 2 different assignments, one for quiz on chapter 3.2 and the other for quiz on chapter 3.3. Okay, so both of those are the chapter sections that we're talking about. So I think I may not have a class period on Monday, and we'll just have the quizzes. Okay, so let's start let's maybe write that down a little bit. So, and then I'll make an announcement and post all this stuff too. And you guys can tell me what you think. So Monday, right, we have a quiz on chapter 3.2 and a quiz on chapter 3.3. Okay, so then I was thinking no class meeting on Monday, right? And then the quizzes will be available starting class time. So you can show up at 10:30 and then take the quizzes, upload them, and then be done. If that doesn't work, it'll be a 24-hour window, so you can do it at that point. There we go. All right, so Monday, no class meeting, but we'll have 2 quizzes, right? And then the quizzes will be available during the class time, which you are free to start. Are you still having office hours today? Yes, I am having office hours today. Also on Monday, your homework is due. This is chapter 3.2 and 3.3. So let's do it midnight on Monday, okay? Then on Wednesday, this is all next week, by the way. So Wednesday, normally what we do when we're meeting in class is to have the presentations for the project. But what I'd like to do is have the presentations for our project now. And it can be really informal. Okay, you're not being graded on your presentations, but what I can do is I can either share a screen or, we'll just set it up as a tile. And then like in terms of like our meeting time, and then whoever goes, we can, choose an order, you guys can decide amongst yourselves what order you want to do, but we'll do project presentations. And that's really informal, okay? That's you saying, hi, my name is so-and-so, and this is the nature of the project that I did. I decided to do this because then you just kind of describe why you were interested in this. Then you can describe like what types of things, what types of algorithms you used and how you implemented them. And then if you actually have like stuff that you want to share, we can share screens, and then you can show that to the class. So the project presentations are short, 5 minutes, no more than 10 minutes, and then that's it. So project presentation, I think it could be fun. And but don't worry, you're not being graded on your presentations, you're being graded on your project. Okay, so Wednesday also our projects are due. And then don't forget your P set 3, problem set number 3 is due. Okay, that's been posted for like a while, right? So our problem set 3 is due on Wednesday. That's all calculus stuff. So you're free to ask me questions about the problem set, in office hours. If you want to come and ask about that, we can talk about it, but that's due on Wednesday. That'll be due like Wednesday at midnight, okay? And then the project write-up I'll take Wednesday at midnight as well, okay? If you want to ask me about what we expect for the project write-up, we can talk about that too. But it's all, I think the project description has a lot of stuff about what to expect for the write-up, okay? So this is what I'm thinking. So no class on Monday because we'll have our 2 quizzes, okay, during the class time, but your homework is due at midnight. Your homework is due at midnight on Monday, and the quizzes will still be a 24-hour window of availability. Then on Wednesday, we'll have presentations where everybody shows up. Each person talks 5 to 6 minutes, and then PSET is due on the 7th. The 7th is, oh, I didn't change my calendar. 7th is Monday. We can change that to Wednesday. Do you guys want the PSET to be due on Monday or Wednesday? It's up to you. What would you guys like? We can vote. Want it Wednesday? Okay, I get 1 vote for Wednesday. Anybody else want it on Wednesday or you want it on Monday? If I don't hear from anybody, doing the PSET can help you prepare for the quizzes, just as a just to let you know. But it can be a lot of things that are due all in one day. PSET's due. I'll change this date, so change to Wednesday, to the 9th. Okay. I had it in my mind it was the 9th, but I'll go and change that. So we can make the problem set due on Wednesday instead of Monday. Totally fine with that. But the projects are also due on Wednesday too, so that's a lot of stuff that's coming due. It's a lot of assignments for one day with the quizzes. You mean like with the homework and stuff in the PSETs? Yep, I totally agree. So I'm okay with the stuff, but the class ends on Wednesday. Can you believe it's a week from today our class is done? It's hard to believe we're coming up on the end of the semester. And don't forget, I'm supposed to remind you, if you guys enjoyed the class, you felt like you learned something and you liked my teaching style, then please go on to the TRACE report. The department actually does look at that and say good things about the class, about me. I'd really appreciate it. If you have constructive criticism too for how I can do it better, next semester or subsequent semesters, you can write that too. But I welcome your constructive criticism, and certainly if you've got positive things to say, please go on to the TRACE reports and write those out too. Okay, so I'll put out an announcement talking about next week. Okay. Okay, a lot of things coming up. All right, so with that said, let's go ahead and start talking about chapter 3.3. Chapter 3.3, our last chapter. Okay, so chapter 3.3, and I have my lecture examples for chapter 3.3. We have a classwork for 3.3 as well. So we'll see how much we get through today. So chapter 3.3 is called Differential Equations and Euler's Method. This is the same Euler that we talked about before when we talked about Euler's angles. He was a big mathematician, so did a lot of stuff. But it looks like Euler, but it's pronounced Euler. All right, so let's talk about what we're dealing with here. So a differential equation itself is an equation with an unknown function and, oops, sorry, I can spell it, and its derivative. Okay, and so I've got a function and its derivative. They're all in the same equation. Okay, so the goal on this, the goal is to find what the function is. Okay, so let's talk about, I can say, for example, if I say d dt, right, we're going to take the derivative of our velocity, and I give you 0, 0, minus 10, right? So I give this to you, and I say the derivative of my velocity is this. Remember, our derivative of velocity is our acceleration, right? So if I say my acceleration is equal to minus 10, the goal, our v of t, is an unknown function. We were doing this last time, right, where we needed to integrate this in order to figure out like what our velocity was, our velocity function is as a function of time. We needed other information like initial values and stuff in order to figure out what this function is. Okay, so this is just a quick example, just to kind of show you that we've kind of been thinking about it already. So let's think about how we would describe stuff. So if I say in differential equations, I call something the first order. If I describe a first order differential equation, that means I have a first derivative inside my function. So which we would think of as dy dx or dv dt, things like that. First derivative is the highest order derivative. I mean, in theory, some functions I can take the second derivative, third derivative, fourth derivative. I can go on and on, right? Some functions have like an infinite number of derivatives. So it's helpful to say, what's the order of this differential equation? We look at our highest order, our highest derivative term. So if I have a second derivative inside of my function, I call it a second order differential equation. If I have the first derivative inside my function, I call it a first order differential equation. So I would say something like y prime of t equals g of t, right? So y prime, that's my first derivative, equals some function, right? So my goal here, I'm going to find, the antiderivative, which means I'm going to take the integral, right? Find the antiderivative to solve the equation. So we've been doing a lot of this stuff as we go, right? We've been kind of doing this whole process as we go. And now we're going to pull it together and talk about, like, why do we care? What's this important? Okay, so our generally speaking, I can write something like y prime of t equals g, which is a function of y and t, right? So g is this function, but it's a function of my function, what's the antiderivative here, and of time, okay? So we have different types of models that we that use differential equations to describe them. So I'm going to go through a couple of different types of models to talk about like what their differential equation looks like and when they're being used, okay? This is just so you know in your mind. So differential equations are used to describe sort of a general class of functions, describe different models. So we want like a general class of functions. And these often describe things in the real world, right? So differential equations actually describe a lot about like biological processes in the body and the brain. We can use differential equations to talk about like population growth or decay, things like that. That's what I'm going to do right now. So the first one that we're going to talk about is what we call a growth or decay model. Okay, so the first thing that happens is, I'll just draw this out. Here's my x-axis, here's my y. This is a growth model. And it's growth because as x gets bigger, y gets bigger. Okay, so it's a growth model. My function is increasing, right? If I do something like xy, and I do something like this, I'm not drawing this very steeply, but this is a decay model. Okay, so it's decreasing, right? So often what happens, the growth or decay model ends up looking like y prime of t equals some constant k times y of t. So the function is equal to its derivative times some kind of a constant. Right, so let's write that down. So the function y of t equals its derivative with a constant multiplier. And that constant multiplier can be equal to 1 or can be some, number. Okay, this is typically exponential. Right, remember exponential functions are in the form y equals b to the x. Right, our variable x is in the exponent where b is our base, right? Base of our exponential. In the real world, when we talk about biology, when we talk about the world around us, the natural world around us, our base is typically E. E is it's a number, it's a transcendental number. It's like pi is a transcendental number. E is like 2.718, so on and so forth. So if I look at my calculator, see this e to the x button. So if I just do e, it's like 2.718. It goes, and this is just my calculator's rounding. It goes on and on forever. Like pi goes on and on forever. So this is e. E stands for Euler, by the way. He's the one who came up with it, who discovered it. Okay, so it's typically e. So our exponential functions, this is like y equals e to the kx. This is y equals e to the minus kx, right? It's a decreasing model. This is an increasing model. Exponential models are important because small changes in x lead to huge changes in y. We can see that with viral spreads, right? So viral spreads are going to be like, at some point, it's all very slow growth until we reach some, critical point, right? Where now my tiny little changes in x are going to lead to really, really huge changes in y. Okay, so this is what we're talking about here. So let's write that down. Small changes in input, which we've thought of as x, lead to very large changes in output, which is our y, right? So it's because it's an exponential, I raise it to that. So where does this get used? This gets used in what types of real world things do we use this in? We use this to model population growth. This is this is all k is greater than 0, population growth or decline. Okay, where k is some positive value. It's our initial value that we're starting with. I can use it to talk about compound interest, like on a bank, right? I put money in a bank and I gain interest on it. So this is compound interest. This is money earning interest over time. Okay, that's an exponential model. Okay, depending on your rate of compounding and whether I compound it quarterly, daily, annually, whatever, it's going to be, my equation is going to change. So compound interest is a growth or decay model. We also have radioactive decay. Right, radioactive decay. I've got some isotope of plutonium. It takes, a million years for it to go half-life, right? It's going to decrease from, 5 grams to 2.5 grams. It takes 1 million years, or whatever the radioactive decay constant is for various isotopes, right? And in this case, K is less than 0. So it's a decreasing value. Yeah, Kx. So anyway, okay. So these are types of things in the real world where we actually use exponential functions to describe stuff, okay? Our growth or decay differential equation is the derivative is equal to some constant multiplier times the function, right? Where our function, I can even write it in a little color here, where our function, say y, for example, equals e to the kx. Y equals e to the kx, okay? Or kt, I think in this, we're using t as a variable, kt. Okay, so when I take its derivative, I've got k as a multiplier out in front. Okay, so our growth or decay model, it's important. We use it a lot in the real world. Okay, model 1. Let's talk about model 2. Model 2 is what we call a logistic function. Okay, so what I'm showing you when I give you y prime equals, this is like basically saying this is the general shape of our differential equation. Okay, so logistic function ends up looking like y prime equals y times 1 minus y. Okay, so this is my dy dt equals y prime. So my logistic function. My logistic function is something like, here's my x-axis, here's my y. Logistic functions have an S-shaped curve. Typically they go like this. And then there's what's called this value here. These things are asymptotes, right? So that the function comes up really close to that value, but it doesn't get above it. It kind of plateaus at that value here. So this is what we call, in a logistic function, we call this the carrying capacity. We often talk about that in terms of population growth. So when we talk about, we think of population growth as being this exponential. This is an exponential based function, right? This exponential e to the something is in the denominator. So it maxes out at the carrying capacity. What happens is our population will increase until, and it increases exponentially until it runs out of resources. We're starting to run out of food, we run out of land, we run out of water, and then the population reaches a maximum. So carrying capacity is a really important concept because it gives us an upper limit essentially on how many people or or yeast, or yeast particles that can live in a petri dish, things like that. So what's our carrying capacity of bacteria in a petri dish? How much can we have growth until it runs out of food, right? And so often what happens is you'll have like cycles, right, where you'll reach this and then, whatever the population will start to die off because it's run out of food, and then it will, you don't want to live at your carrying capacity. You certainly can't go above it because then people start to die off, right? So this is sigmoid. It goes up like this, or it looks something like, I can start off at a higher value and then S-shaped down this way, sort of depending on, the questions that you're being presented with. But our general form for the logistic function is the derivative equals the function times 1 minus the function. That's our, this is for, it's used to describe population growth with a carrying capacity. Right, and we also use this to describe spread of disease. Right, so why is the spread of disease with a carrying capacity? Because we have a certain number of people within a given population. These people can all become infected with the disease. So we have an increase. A lot of people start getting infected, right? But then ultimately everybody's infected who's going to get infected. And so we can't infect anybody else with the disease. So the disease levels out, right? Because it can't infect anyone else. So it's a spread of disease model. We use logistic in order to do that. Okay, this is called a sigmoid. I'll just write that down in a different color. So this is a sigmoid curve. It's S-shaped, roughly S-shaped. Okay, logistic function. let's see, we have also, I'll write this down too. This is our, we'll do an example like this too. This is called a balloon. We're actually going to do this example out from the previous section where we have related rates, right? So radius of the balloon changes as a function of the volume, which is also changing at a given rate, right? So we say dr dt is the thing that we're looking for, and that's 2 over pi r squared. We're actually going to do that. We'll do that example out later, which is why I'm writing it down here. Okay, so we need to have a numerical method for being able to process these things, right? Because differential equations can be, you know, complicated, right? So we need numerical method, which is going to help us to process a differential equation. Right? So it's going to give us an answer in terms of numerical values. Okay, that's of our solution at very specific points in time. We call that like our delta t. So delta t, so I could say every 1 hour, take a pulse check, get some data, and every next hour, do you take a pulse check, get some data. Or I can say every minute, right? So a minute is going to be much finer grained, or every second, or every nanosecond. So depending on my delta t, I can get a lot of information, or I can get, you know, a few points here and there just to get a general picture. Okay, so these are going to help us with simulations. Okay, and that leads us into Euler's method for calculating out numerical methods to solve differential equations. Okay, so let's talk about Euler's method. All right, so Euler's method to work through differential equations. Let's remember, I'm going to say x prime of t, my derivative, equals g of x, comma t. X is just a function, right? It's a function of, say, time, for example. So I've got g of t, which is a function of x and time, okay? So let's write out let me write this out and then we'll talk about the different pieces of it. So I'm going to say my derivative, my x prime of t, is equal to g, x, and t, which is approximately equal to x of t plus delta t minus x of t all over delta t. This is our difference quotient. This is our definition of the derivative. Let me write that down in a different color. When we first started talking at the beginning of chapter 3, so chapter 3.1, we defined our derivative, right? We defined, it was the slope of the line. So the function, I calculated as a slope between 2 different points, t and delta t, and then I went a certain distance, t plus delta t, right? And I calculated my function values and I divided it by that overall difference, delta t, difference quotient. So this is our definition of derivative, right? This is our slope of the line between these points here, okay? So what I'm going to do is I'm going to rewrite this, right? I'm going to multiply delta t times g of t, right? And then, but this is actually delta t times x prime because g of t equals x prime. So let's multiply both sides by delta t. So I'm going to get x prime of t times delta t equals, let's do this, x of t plus delta t minus x of t. I'm going somewhere with all this, so bear with me here. Okay, so now what I'm going to do is I'm going to solve for this. Okay, so let's rewrite it. I'm going to say x of t plus delta t equals x of t plus x prime of t times delta t. Now this is my equation right here. Let's talk about what we're dealing with. This is my Euler's equation, okay? So let's write down our different pieces. So x of t plus delta t. So what does this mean? This is our new t value, because this is t plus delta t, is our next step up. So this is our function at the next step in our time. Okay, so I'm here currently. I want to predict where's my function going. Okay, this x of t is the function value of where we are at right now. Function value at current time. Where am I at right now? That's x of t. How do I know where I'm going to be? Because I know where I'm at right now, that's x of t, and I know where I can predict it because I've got the rate of change times my little time interval, right? So I'm going to go x prime of t times delta t. So this says this is our rate of change. This is our x prime of t times our little itty bitty time delta time. So our time interval that we're looking at, right? So how I'm going to increase, I'm going to increase 5 meters per second, and my delta time is over the next 1 second, right? So if over 1 second, if I increase 5 meters per 1 second, over 1 second, I'm increasing 5 meters. So I'm currently at 10. I'm going to increase 5 meters in 1 second. I want to look at what's my position, what's my velocity in the next 1 second. I'm going to go 10 plus 5. I'm at 15. So this is like we're using our current and our rate of change times our delta t, adding these together to give us where we're going to be at in the next time interval, right? So that's what all of these different pieces mean, okay? What I need to start with, I need an initial condition. What's our present course? Where are we right now? So this would be x of t naught, right? T at 0. Where are we starting with? Okay, so we're going to use this equation to propagate. We're going to keep calculating for all these delta t values to propagate and calculate x of t plus delta t for a certain number of delta t's, right? So how fine grained do I want to have? Do I want to just check it every hour? Or do I want to go like every second or every nanosecond? So that delta t is going to determine how fine grained we are. The finer grained you are, the more detailed your response, the better your simulation. Okay, so now to find x of t at a later time. That's what this is. X of t plus delta t is x of t at a later time. Okay, so we can graph this. Graph x of t plus delta t, our answer. And what that will mean is when we graph this Euler's equation, this is going to be an approximate solution to our differential equation. Okay, so if I use smaller step values, that's our delta t, right? Then I can get higher accuracy. in our graph, which is our approximation. Okay. And I should say, let's do this. It's like approximately equal to that. Okay, so this is your Euler's equation. We're going to use that over and over and over again when we do our examples. Okay. It's a lot to think about, right? There's a lot of stuff going on, but we can do it. Okay, so we want to use Euler's method to find, I'm on my lecture examples. So I'm going to use Euler's method to find x of 1.3. If x of 1 equals 1 and x prime, so they're defining x prime of t for me. X prime equals x of t minus t over 4, okay, with delta t equals 0.1. Okay, so my t is 1. Okay, my delta t is 0.1. Okay, I've got an initial condition right here at x of 1.3, and we're going to use that to fill out our table. So we start off with our initial condition tells us what's our initial, I'm starting at t equals 1.0. I was given my initial condition, x of t equals 1. So let's remember, I'm going to write down our Euler's equation here too. So let's write down at the top, Euler's equation is x of t plus delta t equals, approximate equals, x of t plus x prime, oops, x prime of t times delta t. Okay, so we're given our x prime, right? And I'm going to use those. I've got this very first value. I'm going to plug that into there. So let's go ahead and we're going to work it through. I'll do all the steps out so we can see it, right? So I'm looking at t equals that. And so I need to figure out my first x prime of 1. So what's my x prime of 1? I'm going to plug it into here. Is equal to, oops, x of 1 minus t equals 1 over 4. So this is going to be equal to 1 minus 1/4, which is 3/4, which is 0.75. I'm going to, so this is 0.75. Okay. Now my delta t says it's 0.1. So I'm going to go, my t equals t from before plus delta t. So this is going to be equal to 1 plus 0.1. So my next delta t is, my next t is 1.1. Okay, so now what I need to do is I have to use Euler's equation to help me calculate x of 1 plus 0.1, that's t plus delta t, so 1.1, is going to equal to x of t, 1 plus x prime of 1 times delta t. Okay, so we're going to fill in the blanks. So that's going to be equal to, this is 1 plus, right, my x prime is 0.75 times my delta t is 0.1. 1 plus 0.75 times 0.1. So that gives me x of 1.1 is equal to 1.075. Okay, and that goes right here, 1.075. Okay, now I need to calculate out my derivative value at 1.1 so I can use that to calculate my next prediction. So I'm going to say x prime of 1.1, right? I'm going to use this right here. So this is my derivative. X prime of 1.1 equals x of 1.1 minus 1.1 divided by 4. Okay, because t, my current t is at 1.1. That's what I'm plugging in. So x of 1.1, 1.075 minus 1.1 1 divided by 4. So this thing is equal to 0.8. Okay. All right, so let's calculate out our next t value. We're going to increase our t by 0.1. So this becomes 1.2. So I'm going to calculate x of 1.2 equals, I'm going to say, I'm using my Euler's equation. X of 1.2, that says t plus delta t. So this is x of 1.1 plus x prime 1.1 times delta t. Okay, so this is x of 1.1, right? So this is 1.075 plus my x prime 0.8 times my delta t, which is 0.1. Okay, see how I'm just plugging things in. Again, I'm looping through essentially. When I add that up, I get this is equal to 1.155. That 1.155 goes right here. And I use that value to calculate out my derivative. That tells me my rate of change for the next. You have to keep going until we get to x of 1.3. So let's calculate our derivative of 1.2. So our derivative says x of 1.2 minus our time divided by 4. X of 1.2, 1.155 minus 1.2 divided by 4. So this is going to give me 0.855. I take that value and I plug it in here, 0.855. Okay, here I need, this is where I'm going to stop. So this is going to be x of 1.3 equals my Euler's equation, right? So this is x of 1.2 plus x prime of 1.2 times delta t. Okay, so x of 1.2, 1.155 plus my rate of change, 0.855 times 0.1. Okay, my x of 1.3 is 1.2405. And they said that's all they wanted, x of 1.3. So that's actually my final answer. Right, because they said find x of 1.3. So I'm done. Okay, I looped through. Okay. It's kind of tedious, right? There's a lot of like, you've got to plug it in, you've got to keep track of your old stuff. I like the tables and I do, you can see my work, I do all of this stuff out. It helps me keep track of all the bookkeeping. And so then I don't lose my place. Okay. Let's do example number 2. Same kind of method. Use Euler's method to solve y prime. So remember, we're solving. So this is, we're given, we've got our derivative equals our function. So derivative equals function, that's an exponential. We know that, right? So we've got an initial condition, right? We're told to keep our t values, or we're going to start at 0 and we're going to go up to 0.5. So we only have 5 values that I'm doing. So I can even populate out. So t starts at 0. My delta t is 0.1. So I'm going to go 0, 0.1, 0.2, 0.3, 0.4, 0.5, because they said keep t less than or equal to 0.5. So I know I can populate out all those values. So let's remind ourselves Euler's equation is going to be, I'll write it out here. So this is y of t plus delta t equals y of t plus y prime of t times delta t. So this is our Euler's equation. Right? And we're given a value for the derivative. We're given an initial condition for our function. And we're going to use all that to help us prime it. Okay. So let's go ahead and do it. So our y of 0 is equal to 1. We were told that. I'm going to calculate out my derivative. So my y prime of 0 equals y of 0. I was told that right there. So that's equal to 1. Right? Because my y of 0 is equal to 1. So therefore, my derivative at 0 is equal to 1. Now I need to use my Euler's equation to calculate out 0 plus 0.1. Give me y of 0.1. So that's going to be, Euler's equation says, our current value, y of 0 plus y prime of 0, excuse me, times delta t, which is equal to y of 0, 1, plus 1 times delta t, 0.1. Okay, so this is equal to 1.1. Now we were told y prime equals, right? Y prime equals, so y prime of 0.1 equals y of 0.1, which is equal to 1.1. So I'm just going to plug in that. Okay. Our next bit our Euler's equation. So 0.2 is going to equal y of 0.1 plus y prime of 0.1 times delta t. See how I'm looping through my Euler's equation? I'm using this each time. This is what I just did. So y of 0.1, that's 1.1, plus 1.1 times delta t, which is 0.1. And that's going to give us y of 0.2. This is going to give me 1.21. 1.21. My y prime, 0.2 is equal to y of 0.2, so 1.21. Okay, let's do this. I'm going to draw a little line so we can keep track. So this is our next iteration. This is our first iteration. This is our next iteration. Now we're going to do another one. A lot of numbers and equations floating around helps to delineate them. So I'm going to go y of 0.3. Euler's equations again, okay, which is y of the previous one, 0.2, plus our derivative of the previous times delta t, which is equal to y of 0.2, 1.21, plus our derivative, 21 times 0.1. And that was going to equal to 1.331. 1.331. Our derivative equals our function. We were told that, so this is 1.331. Okay. My next one, y of 0.4, almost there, is equal to y of 0.3 plus y prime, 0.3 times delta t. So let's plug it in. Y of 0.3 is 1.331 plus my derivative, 1.331 times my delta t. Okay. When I multiply it all out, I got 1.4641. I'll put that right here, 1.4641. My derivative is equal to my function. So that goes right there. Okay. Our last one, y of 0.5, right? Because that's our last one. So we want to go y of 0.4 plus y prime 0.4 times delta t. So let's plug in what we know. 0.4, so it's 1.4641 plus 1.4641 times 0.1. In that one, I got 1.6105. Okay, and technically I'm done. I don't have to fill in my derivative, which I can because they told me. Right, they said the derivative is equal to the function, so I can just fill it out. Okay. It's not so hard, but it is kind of tedious, right? Give you guys a minute to finish writing that, and then we'll do example 3. Then tomorrow we'll finish up this chapter with a couple more examples, and then I'll do classwork. Okay. So example 3 says, use Euler's method to solve the logistic function. So we're given, look, our derivative, y prime equals y minus y. We can recognize this. We were told that's a form of logistic. We have an initial condition. We want to keep it under 0.5, and we want our delta t to be 0.1. So again, I can fill this out. I'm starting at 0, 0.1, 0.2, 0.3, 0.4, 0.5. They told us to stop t less than or equal to 0.5, so I don't have to go on forever. You can imagine I'm going to write a computer program. I'm going to loop through for t equals 0 to 0.5. You know, every time I loop through, I'm going to say t equals t plus 0.1, and that increments my counter, right? And so then I'm just going to calculate all these functions. So let's remember again our Euler's equation. I'm going to write it down. So y of t plus delta t equals y of t plus y prime of t times delta t. So this is Euler's equation. This helps us calculate out the next bit. Now, we have an initial condition y of 0 equals 1. I'm going to fill that out. I'm going to calculate my derivative first, okay? So now I'm going to go y prime of 0 equals, that's a 0. Y prime of 0 equals y of 0 times 1 minus y of 0. Let's fill in the blanks. So this says y of 0, that's equal to 1, times 1 minus 1. So that's actually equal to 0. Right? Did I do that right? I think I have, do I have a typo? Oops, I have a typo here. I apologize, folks. This should be actually 0.5. Otherwise, we're just going to get zeros the whole way down. So this is a typo. I was wondering about that. Sorry. Let's fix that right now. So my typo, and let me write that in black. Y naught equals 0.5. Good. Great. So then that's gonna, I'll change this out too. Whiteout is very helpful. So 0.5 minus 0.5, and that's going to give me 0.25. And let's change our table. So this is equal to 0.5. Okay, 0.25. Okay, is our derivative at 0. All right, calculated that. It's good to catch the typos. Okay, so now our next round, okay, we want to calculate y of 0.1. I'm going to use my Euler's equations. So I'm going to go y of 0 plus y prime of 0 times delta t. Okay, so let's fill in the blank. So this becomes y of 0, that's 0.5, plus y prime of 0 times 0.1. Okay. This becomes 0.525. Okay. Now I need my derivative. So y prime of 0.1 is going to equal to y of 0.1 times 1 minus y of 0.1. Let's fill in the blanks. So y of 0.1, that's equal to 0.525 times 1 minus 0.525. And that was equal to 0.2494. So look, our derivative is decreasing. It's a smaller value. Oops, that's a 2. 2494. Make that look better. 2494. Okay. Let's calculate our next value. So I'm going to go y of 0.2 equals, my Euler's equation says y of 0.1 plus y prime of 0.1 times delta t. So let's start plugging in. So my y of 1, 0.525 plus 0.525 times 0.1. Okay, that's going to give me 0.5499. Okay, and so on and so forth. Okay, I'm going to fill out the table. I'm going to skip all the rest of the algebra, right? But I'm going to fill out the table here. So this is going to be 0.2475. This is 0.5746, 0.2444, 0.5991, 0.2401, 0.6231, 0.2348. Okay. So I would be plotting my y of t. Okay. Let's write that down. I'm going to plot y of t, and that's going to give me values. It's going to show me stuff. Okay, let me make this look better. Okay. I didn't go through and do it, but I can. Okay, all the rest of it is just algebra. I'll write up the rest of it before I scan it in. Okay, you guys? Any other questions so far? Are we good? If we're good, then we can end early, okay? Because the rest of it is just algebra, which I'll write up and then I'll scan it in later. I'll scan it in tomorrow after I finish it. Okay. Okay, guys. Right. Have a great day, you guys. See you tomorrow. I'll post an announcement about what to expect next week.